One of the things I'm trying to do as I work through the problems in Arthur Engel's book called Problem Solving Strategies is when I take quite a long time to find a solution, and the solution in the end is one that I feel I should have found reasonably quickly or more quickly than I did. I try to think a bit about where I went wrong. And of course, if I found a solution, that doesn't mean I mean where I went wrong strategically speaking. So what did how did I end up going down a path that I shouldn't have gone down? And it's just happened with a problem um, that took me quite a long time. And I did find a solution, but somebody commenting on the video, um, actually, it seems not nice if I don't quickly find the name of that person. So while I'm talking, I shall look that up. Um, anyway, somebody commenting came up with a solution that was nicer than the one I'd come up with, and one which I thought afterwards, reading it, maybe one could say I should have found. And so I actually would like to. Oh, sorry, I would like to describe that solution. Okay, so the person concerned is called Aaron Marcus, and so the question was. I'll just discuss this very briefly before I get on to some new ones. You take the numbers 1122 all the way up to 1998, and the question is, can you order them in some way so that between any two occurrences of the same number, if it's m, say, there are m minus 1 numbers in between? Or put it, an equivalent way of saying that is that the two m's for each m will be exactly m apart in the sequence. And I did eventually come up with a solution, but what I never really quite did in a nice way was to think, what process could I think about and what could I prove would be an invariant of that process? And in retrospect, had I put a bit more effort into just trying to think, in what sense is this an invariance question? I think I would have got there much more quickly. And let me just show you the solution that Aaron Marcus came up with. He said, let us, so that we're trying to turn this into some other sequence that's permuted. So a natural process to consider when you want to turn one permutation into another is transposing two adjacent terms in a sequence. So we know that any permutation can be achieved as a product of transpositions of two adjacent things. And so if you want an invariant, you could just try to look for something that doesn't change whenever you switch around two things that are next to each other. And the final piece of data that we've got is that the number of things between the two m's is m minus 1. So we have information about how many things there are between any two m's, and we have that for each m. So it's natural to think about some invariant connected with the numbers of occurrences of numbers between other numbers and that sort of thing. So if we define for a sequence, we define, let's say, Rm equals the number of numbers between the two m's, then initially we know that every single Rm is 0, and at the end we know that every single Rm is m minus 1. So it then becomes very, very natural to try to find something that doesn't change connected with the Rms. So let's just think about that. Supposing I swap a 2 and a 3, then so sort of 2, 2, 3, 3, say, right at the beginning, let's say. Supposing I swap that 2 and that 3, then the distance between this 3 and this 3 changes by 1, and the distance between this 2 and this 2 changes by 1. So we add 2 to the total. Now, suppose in general, supposing I had sort of R and S, I don't know whether the other R is on this side of the S or this side of the S. So perhaps it's over here, and perhaps the S is also over here, or something like that. Then, if I swap them, the distance between the two S's goes up by 0, and the distance between the two R's goes up by 1. I mean, the distance between two R's goes down by 1. So in that case, we add 0. If I had the S over on this side, then the two distances would both go down by 1, and then it would be -2. But what we notice is that in every single case, the change to the sum of the differences is an even number. And that turns out, I'm not going to do a calculation, but it turns out that that is enough. You just have to look at the parity of the sum of m minus 1 as m goes from 1 to whatever your n is. And a parity argument then finishes off the proof. So that was a really lovely solution, which I think I would have had a good chance of finding quickly had I thought about trying to find a process that was invariant when you converted, sort of during some natural process of converting this sequence into the sequence with the property that you're supposed to have. So, chastened by that experience, now let me move on to the next question. And we're on piles of chips again. So we've had those sorts of questions several times. What is it this time? So initially, we have 3 piles. I'm not going to write the whole question out this time. We have 3 piles with A, B, and C chips, respectively, it says, but I don't think the word respectively contributes much. In one step, you may transfer one chip from any pile with X chips onto any other pile with Y chips. That seems okay. One chip from any pile with X chips onto any other pile. It's not quite clear whether X and Y are some fixed numbers or they're just the numbers that you happen to have in the 2 piles you choose, but maybe that'll become clearer. Let D, it looks as though they are fixed numbers, so let D equal Y minus X plus 1. Oh no, wait a minute. So if D is greater than 0, the bank pays you D dollars. And if D is less than 0, you pay the bank mod D dollars. I think that's a slightly, I'd just like to say whatever D is, the bank pays you D dollars, and that might be a negative amount. Repeating this step several times. Oh, I quite like the question. So repeating several times, you observe that the original distribution of chips has been restored. I'm a bit puzzled by this question, but let's just see what maximum amount can you have gained at this stage. I can't see how it could be anything other than 0, but let's just have a look. Can you have gained at this stage? So why do I say that it can't be anything other than 0? It would seem that if it could be if it can be anything other than 0, supposing it could be some positive number, then why don't you just do some transformation on ABC, gain a bit of money, and then just repeat that transformation over and over again. And if you don't want to repeat that transformation, then why not just do something first, and then get back to that new thing, and then get back to the original. So it would seem to me that the answer ought to be 0, but let's just think about that a bit further. On the other hand, we've got this +1, which puzzles me slightly, because that seems as though you're gaining as you go along, on average. So let's just try to understand. So if you start with ABC, and I do a whole general move, I might as well take 1 from the A pile, add 1 to the B pile, and how much do I gain if I do that? The gain is B minus A plus 1. And then if I just go straight back, I'll gain A minus 1 minus B plus 1 plus 1. And what happens if I add those two together? I get minus 1 minus 1 plus 1 plus 1. I get a grand total of 0. So it's as I expected. So could it be just that the number, that the sum of A and B and C and the amount you've got in the bank remains constant? So I would like to have used D for the amount the amount I got in my wallet or whatever, but D has been taken, so let's call it N. So what happens after oh no, wait a minute, that will not remain fixed, because A plus B plus C is fixed, so that can't be the invariant. So what? But there must be something simple like this, I think. But what could it be? So what happens on the first? So I start with, let's go back to this. I start with A, B, C, and N. I just want to find something that doesn't change when I replace that by A plus 1, B minus 1, C, and N plus B minus A plus 1. And that is a bit strange. How can I make B minus A plus 1 out of A plus 1, B minus 1? So B minus 1 that is quite strange. doesn't look as though it can be some linear combination of A, B, C, and N that's remaining fixed. So what else could it be? What happens if I look at something like AB? So that's just what's happened to A times B when I've done this. It's turned into, it went from AB to AB plus B minus A minus 1. So it added B minus A minus 1. Oh, but I did something wrong there. I've transferred from, here I transferred from B to A, so I should have put A minus B. So now I've added B minus A minus 1, but here I've subtracted B minus A minus 1, so it looks as though it's the product plus the amount I've got in the bank. So I think I've managed to find an invariant. So I had a little inspired moment there. Unfortunately, I always hate it when that happens. And I'm unable to say terribly easily what led to that sudden realization, but it was connected with realizing that a linear combination wasn't working, and that it should somehow, the amount depended on A and B in some sense, and so the more the difference between A and B was, the more things were going to change, and that kind of ended up leading to the idea of considering the product. So I think my proposed invariant is AB plus BC plus AC plus amount that I've got in the bank. So just if I've transferred from B to A, then I've added 1 to B, and I've subtracted 1 from B, and I've added 1 to A. That doesn't, so this is unchanged, BC plus AC, because B plus A is unchanged. AB turns into AB plus B minus A minus 1, and N turns into N plus A minus B plus 1. So this sum does remain the same. So at the end of the whole process, if I've got the same distribution as I had in the first place, then AB plus BC plus AC is back where it was in the first place, and therefore N must be back what it is in the first place. And so not only can you not have gained, but you cannot have lost either. And in fact, the argument that that was bound to be the case, the argument that it was unlikely that you'd be able to gain, because otherwise you could just gain indefinitely, applies equally to losing. Okay, so that was quite nice. Next one, 55. Let dn be the digital sum of n in n. Oh, I see. So the sum of the digits. Solve. Oh my goodness. This I was not expecting. N plus dn plus d of n equals 1997. All right, well, I suppose an immediate observation is we know that dn agrees with n mod 9. I might as well say the strongest thing I can. And d of n agrees mod 9. What is 1997 mod 3? It is not a multiple of 3. Because 1 plus 7, using the digital sum trick, is 8, which is not a multiple of 3, and those two are multiples of 3. So it would seem that the left-hand side is a multiple of 3, the right-hand side is not a multiple of 3. So I think my answer to this is, sorry, I can't. And I think that's the intended answer. So maybe one could say I've solved it in the sense that I've found the solution set, and the solution set is the empty set, unless I'm making some very, very silly mistake. But that really does seem correct to me. So that wasn't a very interesting question, unfortunately. Help. I've got one that says MMO 1995. So that must be a something maths Olympiad. Actually, I've discovered that there was a key to that. So it may be that I can tell you what MMO actually means. I'll just, if I can't find it quickly. Oh yes, I found a key. MMO stands for Moscow Mathematical Olympiad. Oh, that's a bit alarming. But at least I got the clue that it involves an invariant. So start with 4 congruent right triangles. So this one may take me some time if it's a competition question. In one step, you may take any triangle and cut it in 2 with the altitude from the right angle. Prove that you can never get rid of congruent triangles. MMO 1995. So before I start thinking about an invariant, I just want to think about what on earth's going on. So let's take some fairly kind of arbitrary right angle triangles. I'm putting the right angle up at the top here. I just want to get a feel. It sort of seems as though, you know, can't you obviously do it? Now, if I chop one of these in 2 using the altitude as a right angle, I mean, as taking the altitude from the right angle, then I can sort of chop again, do that, and I can chop again, do that, and so on. Now, this has really got nothing to do with right angled triangles. It's just a tree, really, because 2 triangles are going to be congruent if and only if they've got the... Oh, wait, is that true? Ah, so that triangle has the same area as that triangle. That makes it a bit more complicated. So that triangle and that triangle are congruent to each other. I was hoping that something like that would not happen, but that's clearly the case because I've got a right angle here and I've got a right angle here, so I've just chopped a rectangle in half. So we still need some, I think it can still be turned into a combinatorial type question, but only the, in some sense, only the triangles that are that absolutely have to be congruent are congruent. But what precisely is that going to mean? That may be a little bit trickier. So instead of going into a careful analysis of what precisely happens and drawing sort of trees and saying, just labeling them according to the area of the subtriangle, I think I want to do something a little bit different. And just actually, I think maybe it is possible to do it in that sort of way. But I I want to think, what could an invariant possibly be like? And why start with 4? Why not start with 2? Let me just see whether I can. In fact, the funny thing is that once I've done a cut here, if I do that cut and that cut, then I'm back to where I started, because I've got these two congruent triangles. I'm not back to where I started because I've got 2, but let me just see if I can answer this question about 2 triangles first of all. So I start with 2 congruent triangles. Sorry, there's not a very nice diagram, but they're meant to be congruent. And I do one thing like that. And now I've got 3 triangles, no 2 of which are congruent. So actually, that was a question with an easy answer. What if I have 3 to start with? Let's just check that we still can't do it. So now I've got to do something more. So I'll chop this one like this. Now I have a problem that that one is congruent to that one, so I can cure that by just chopping there. I've also got that this one is congruent to this one, which I can try to cure. I don't want to cut there, but well, that doesn't, by cutting like that. Now I've got, I think my only pair of congruent triangles is those 2. Nope. Wait a minute. Yes, so, yeah. Those 2 are congruent. They're not congruent to this one, so those 2 are congruent. So I'm down to 2, except I may accidentally create another copy of this one. But let's just have a try. So if I cut this one, I think that's all right. So if I cut this one down like that, then it's going to be a bit smaller than that one, because that was the diagonal of this one, but not a diagonal of this one. So that's not congruent to that. That's clearly not congruent to this. Nothing here is congruent to this. That one was not congruent to this, because again this is a diagonal, whereas that's not a diagonal. So I think for 3 one can just about do it. Okay, so I'm now seeing the appeal of this question. So it's got a kind of something running out feel about it, that you're sort of, as you go along, you create congruent triangles and you destroy congruent triangles. But if you start with enough triangles, then you can't somehow compensate for the creation. You can't, the destruction just can't compensate for the creation. This is not an invariant approach, but an observation that I made along the way there was, any cutting method that ever creates 4 smaller congruent triangles, it's not exactly doomed not to work, but it's destined not to be the simplest cutting method. So, because I've got to make those 4 congruent triangles non-congruent by further cutting, and if I can do that, then I could have done whatever I did for those 4 smaller ones to the 4 original ones. So if I make the initial assumption that my cutting method should be minimal, in other words, I use a minimal number of cuts, then that I don't believe it. Oh, sorry, I thought for a second that I wasn't recording. I got a bit worried. So when I said I don't believe it, I was right not to believe it. I am recording. Apologies for that little interruption. So if I assume that the number of cuts is minimal, in theory there might be a non-invariant approach. I'll come back to thinking about invariance, but I would quite like to think about, can I argue that somehow if I forbid myself ever from creating 4 smaller congruent triangles, then I've got into trouble. But I think maybe I do want a combinatorial approach. So this is what I want to do to get it to be combinatorial. So suppose that this side has length 1 and this side has length alpha. And I think I'm going to have to give this length beta. So we know that alpha squared plus beta squared equals 1, but I don't care so much about that. Then when I cut the area, in fact, let's make this 2 just so that so the area of the original triangle was alpha beta. Is this going to be nice? And the area of the 2 triangles that I end up with will be, so it's going to be sort of alpha squared times what I started with, because, oh no, sorry, alpha, okay, I better stick with 1, otherwise it's going to be horrible. So alpha beta over 2. So when I replace this 1 by an alpha, but it's a similar triangle, then it multiplies by alpha squared, so I get alpha cubed beta over 2, but the main thing is I multiply by alpha squared. And when I do this, I will multiply by beta squared. So now let's just normalize so that alpha beta over 2 equals 1. And I'm going to choose alpha and beta to be very arbitrary so that no two of these no two powers of alpha and beta are equal to each other. So now I can multiply by alpha squared, and if I say that phi equals alpha squared and psi equals beta squared, then at each stage I sort of start with area 1, then I can get area phi and area psi. And then the next stage I'll get area phi squared, area phi psi, area phi psi, and area psi squared, and so on. So my question now is reduced, and I feel somehow this will be an easier one to think about. It's reduced to the following. I have a tree. But why don't I just represent that as I can represent that as a point on a grid, really. So maybe not a tree, but as a point. So it's phi psi. So what I can do at any stage is I've got a chip on 1. I can get rid of it and replace it by a chip. So I'm just sort of converting it into the Kontsevich question that I did a few days ago. So my options are always to take a chip and replace it by 2 chips. But unlike in the Kontsevich question, I'm allowed to have 2 chips on the same square. So I could replace that by that and that by that. That's what happened if I'd done 2 stages. But then when I've got those 2 chips on the same square, I've got to, if I want to avoid congruent triangles, I've somehow got to get rid of any pairs of chips on the same square. So this is very similar to the Kontsevich question. That's rather fascinating. So where did that come from? Just cutting a triangle into two subtriangles like that gives you one of area phi, one of area psi, where phi is alpha squared, psi is beta squared. And so that is precisely the operation. And I just turned that thing round so that this point here was a point down here. Perhaps it's going to turn out to be unfortunate that I've chosen the letters phi and psi there. Now, it's easy to see that with one tree, so actually now the question actually is that we've got three chips, sorry, let's just say we start with three chips in the bottom corner, then I'm going to try and do the proof that I did before, but with chips instead. So I moved one of them like that, then I took another one and also put it like that. And then I took one of these and put it like this. And then I took one of these and put it like this. And then I took one of these and put it like this. And lo and behold, I had all the chips in different places. So my guess is that the invariant is going to be pretty much the same as the invariant that worked for the Kontsevich problem. So supposing we start with 4 chips, what was the invariant there? It was sum over all chips of 2 to the minus distance from chip to the origin, where the distance is measured by the number of steps you have to take. So this distance is 0, that distance is 1, that distance is 2, and so on. So what is the, I'm guessing this is going to work. What's the initial value of this? Start with 4, because we have 4 chips at the beginning. And what is the total over the whole of 0, 1, 2 squared? It's 1 plus 2 over 2 plus 3 over 4, so the 3 points at distance 2, and 2 to the 2 is 4, and so on, plus 4 over 8, plus, and so on. And I'm sorry that I'm a little bit, I like to do this in a very gentle way, so I write this as 1 plus a half, plus a quarter, plus an eighth, and so on, plus a half, plus a quarter, plus an eighth, plus, and so on. I just find it easier to plus a quarter, plus an eighth, plus, okay, I think I've written enough. So now I'll sum the columns rather than the rows. No, I won't. The columns is what I started with. Now I'll sum the rows instead of the columns, so I get 2 plus 1, this is beautiful, plus a half, plus a quarter, plus, and so on, which equals 4. So we started with 4. In order to finish, we'd have to fill up the whole of the plane, which would take infinite amounts of time, and therefore we can never do it. I'm extremely pleased with how that went, but it has to be said that I had a huge advantage in that I'd done the earlier question of Kontsevich, which meant that once I'd worked out that it reduced to something very similar about chips and replacing chips by 2 chips, or it could be transformed into that form, I knew exactly what to do. So that's an example of gaining expertise just by simply having seen related problems before. That seems like a very good moment to stop. So I've got 4 questions to go on this sheet, and then I can crack open the champagne. And what a relief that this was. that this was recorded after all. Something very strange going on there, so I can't find the... I think I know what's happened. I think I've done this whole video without sharing my screen. That is going to be a bit problematic. So what I will... Okay. I'd better... I don't know how to do this. So I will carry on a little bit. And just maybe talk through the solutions that I've just been finding. That is annoying. So the question that we started with was, you have 3 piles of chips. In one step, you can transfer a chip from any other pile, and if you do so, basically the gain is going to be, so if you transfer a chip that's got X things in it to a chip that's got Y things in it, your gain will be Y minus X plus 1, whether or not that number is positive or negative. The question puts it in a slightly more complicated way, saying if it's negative, you get minus that amount, but or you have to give minus that amount, but I'd say you just gain a negative amount. If you get back to the original distribution of chips, what's the most you can gain? I wanted to prove that the most you can gain is in fact 0 because there's some invariant. I searched around for an invariant of the number of chips you've got and the amount you've got in your wallet after the bank has paid you or you've paid the bank back. And I couldn't find any invariant that was a linear combination of these, and after a while it seemed as though there was not going to be one. And then I realized that the product, the effect on the product of adding 1 to A and subtracting 1 from B was to add B minus A minus 1, which is precisely minus what you get compensated for from the bank. So it looked as though a good operation was going to be, or a good invariant was going to be the sum of the 3 products plus the amount of money you've got. And it was a quick check that that was indeed the case. And therefore, if you get back to your original ABC, then the original n must have been, you must get back to the original n, and therefore you've gained precisely nothing. So that was that solution. Let dn be the sum of the digits of n. Find all solutions to this equation. I just observed that n and the sum of the digits and the sum of the digits will be the same. Actually, mod 3 is enough. And so this number will be a multiple of 3, but this number is not a multiple of 3, so there are no solutions. And now I'm quite sad that my pictures here were not visible, but let's just quickly talk through what I did. So in one step you can chop a triangle from the altitude to get 2 congruent triangles. You start with 4 triangles, and you want to prove that you can never ever not have at least 2 congruent triangles. So an initial observation, which at first I was not expecting and then I realized was obvious, so to speak, was that if you cut down this line here and then you do 2 more cuts, then this triangle here will be congruent to this triangle here. So you're not getting 4 different triangles once you chop into 4 pieces. And that's basically where the interest of the problem lies. Then I did some experimenting, realized that with just 1 triangle it was very easy to split it into 2 non-congruent triangles. If you start with 2 triangles, then you just chop one of them once, and then you've got that one and that one. With 3 it was a little bit harder. So you had to cut, and then to cut this one and then cut that one once and then cut that one another couple of times, but it all eventually worked out. And so then we moved to 4. When we moved to 4, I thought, okay, it's time to get just to work out what the combinatorial underlying, what's actually going on combinatorially here. So I took a generic right angled triangle, so I have side lengths A and B and 1, and generic would be so that we won't get any congruences that you're not expecting. So for example, if alpha equals beta and you cut down an altitude, then those two triangles will be congruent to each other, but we don't want any coincidences like that, so we just choose alpha and beta to be completely generic, as I say. So let's look at what happens to the area when we cut. Well, here we've got similar triangles. This whole triangle is similar to that triangle. That triangle has a side length, has a diagonal of length alpha, where this one has a diagonal of length 1. So its area is alpha squared times the area of the original triangle. So when you cut, you multiply the area. One of them is alpha squared times the area. The other one is beta squared times the area. And there, by the way, is a quick proof of Pythagoras' theorem, and a well-known proof of Pythagoras' theorem. And so then I called alpha squared phi and beta squared psi, normalized everything so the initial area was 1, and just wrote down what the areas were. So if you cut once, you get phi and psi, and if you cut once again, you get 1 of phi squared, 1 of phi psi, another 1 of phi psi, and another 1 of psi squared. And having done that, I suddenly realized that this was basically one of those things where you can pick up a chip and replace it by one just above and one just next door. And you get that by just rotating the diagram here suitably so that this root is down at the origin of the non-negative integers squared. So we can reformulate it as you start with 4 chips at the origin. Any chip you can pick up and replace, you can remove and replace by 2 chips, one just to the right and one just above. And if you want to have no congruent triangles, then what that says is you've got to end up with all the chips occupying different places. Because that was very similar to a problem of Kontsevich done earlier on in these 60 questions, it was a very reasonable guess that the right invariant to look at was the sum over all the chips you've got of 2 to the minus the distance from the chip to 0, 0, where the distance is the length of the path if you go if you can go vertically and horizontally. So this, for example, has distance 1, 2, 3. So if you start with 4 chips all at 0, their distances are 0, so then you get an initial value of 4 for this invariant. And if you sum up the distances over all chips from 0, you get this quantity here. So there's one thing at distance 0, 2 things at distance 1, 3 things at distance 2, so I've divided by 2 to the 2, 4 things at distance 3, so I divided by 2 to the 3, and so on. You can rearrange this sum. This is called partial summation, what I'm doing here, in that way, and that makes it, so that's 1 plus 2 over 2 plus 3 over 4 plus 4 over 8, and so on. And when you add all these up, you get 2 plus 1 plus a half, which is 4. So the sum of, if all the chips have to end up in different places, then the maximum that the invariant can be is 4, but in order to achieve 4, it would have to fill up the entirety of the grid, which means you take infinitely long to get there. So that's another way of saying you can never, in fact, get rid of congruent triangles. So that's the solution, and I suppose if you look back, you can see myself finding my way towards that solution. Sorry, this is a rather peculiar video, though. My new thing I've learned is not mathematical, it's that I must take a bit more care over the technical aspects of these videos. So apologies for that, and I now will finish.